All right, hello. In this video, I'm going to be going through at least two, maybe all four, probably just two though, of the kinds of reactions and working you through the process of predicting the products. First off, the first one, we're going to do a review of double replacement. You should have this worksheet. If you don't have it, then you can find it and print it. It is worksheet 5.3C. It is linked in Canvas. And I want to go ahead and mention now, I'm trying something new with this. So Google just added the ability to put tabs in docs. And so on the margins on the left side of the doc, there's an option for different tabs. The first tab is the blank worksheet. The second tab is the key. So you can look at the key too online. So make sure you have that before we get started. All right, cool. Now, to review, we're going to do number 1 and maybe number 2 on the double replacement section. Okay, this worksheet has two sides. On the front, it has double replacement reactions, 10 double replacement and 10 combustion. And then on the back, it's all single replacement, but half of them are cation replacements and the other half are anion replacements. And we're going to go through all 4 of these, maybe in this video, maybe not. We shall see. So I'm going to pause this and write out the first reaction, and then we'll be ready to go. All right, first off, I am not going to be writing out all the ions as we go. I'm just going to be going straight from reactants to products, like I did in the end of the last video. So that's how I'm going to be reviewing this. I am going to go through it a little more in depth, make sure that everybody understands what's going on. So first off, cation has to be written first. It has to be ammonium, hydrogen, or a metal. In our first compound here, we have silver, which is a metal, so that has to be our cation. So this is silver, so this has to be the cation. And because it is the cation of the first compound, I am going to write it at the beginning of the first blank so that I don't mix them up later. So Ag goes straight to the first blank because it's the cation of the first reactant. Okay, and it has a charge of +1. Okay, then in the second compound we have ZnCl2. Zn, again, is a metal, so Zn has to be the cation. So I'm going to put Zn over here, and that, of course, is +2. Silver has to be +1. Zn has to be +2 because those are 2 of the metals that you're supposed to have memorized their charge. NO3 has to be a polyatomic ion, so you can look that one up on your polyatomic ion list. It is nitrate, and it cannot go here. Well, why not? Well, because it's already bonded to silver. It's a reactant that was attached to silver. So no reaction happens if we put nitrate here. We have to put nitrate with zinc. So I'm going to write NO3? Yeah, NO3 over here, and it is a -1. Which means that Cl here, because Cl2 is not a polyatomic ion, so this is chloride, Cl, has to go with the silver for Cl, the -1 charge. Now, we aren't quite done. We have to charge balance our products. Okay, so AgCl, well, that's a +1, that's a -1. Those are balanced, so we're good on that one. ZnNO3, though, we have a +2 and a -1. So this is not charge balanced, so we have to swap and drop here, which means we need a parenthesis and a 2 on this NO3. So the products are AgCl and ZnNO3 2. I'm going to go ahead and do... Man, I want to do one with... Well, I guess I'm not. Okay, I'm going to go ahead and do number 2. So I'm going to pause this and write that out, and then we'll go through on that one. I want you to try it first, though. So pause this, try number 2, and then hit play to actually watch it. All right, here we go. Okay, I erased the charges over here because I didn't want to get them mixed up with these ones while I was going through. Okay, so hopefully you already have predicted products for this one. I'm just going to be going through and hopefully confirming what you have. So the cation in H2SO4 has to be hydrogen because it's written first, and since H2 is not a polyatomic ion, we are just going to transcribe the H, and that is a +1 charge. In NaOH, Na is a metal, so Na has to come over here. That is obviously +1. Then for our anions, we have SO4, which is a polyatomic ion, which means that 4 has to come along, but not to the H, to the Na. I'm writing the wrong letter. SO4, and that is a -2 charge, which you get off your polyatomic ion list. Then we have OH, which has to go with the H, and that is a -1. So then for charge balancing, you didn't forget charge balancing, right? You remembered you have to charge balance. HOH is already charge balanced, so hopefully you didn't write anything here. Dang it. Yeah, okay. However, NaSO4 is not charge balanced because Na is +1 and SO4 is -2. Okay, so we have to actually charge balance this one. Now, swap and drop, we need to put a 2 on the Na. You do not put parentheses around Na, though, because Na is not a polyatomic ion. So it's Na2SO4, no parentheses. Okay, from there, you should be able to go through and do the rest of these 10. Pause this, work through those 10, and once you have finished those, then play the video again, and we'll go through the combustion reactions down here. Okay, and for this, I'm telling you them, but eventually you have to actually be able to identify them. So I'm going to point a couple things out. But we'll save that for later. So yeah, I'm going to pause this and rewrite some stuff. All right, I'm not going to make this any more complicated than it is. In order to be a combustion reaction, the products have to, 100% of the time, without fail, always be CO2 and H2O. But that's it. It doesn't matter what order you write them in either. It's the same thing either way. It's always CO2 and H2O. Or H2O and CO2. I don't care what order you put them in. Generally, though, I will say you're probably going to see CO2 written first. Heads up. Okay, now, what's more important with these is you need to learn what you're looking for. You need to learn what you're looking for to recognize a combustion reaction, because a combustion reaction can look like a single replacement reaction if you don't know what you're looking for. Okay? Red flags should fly in your head every time you see O2 by itself in a reactant. Okay, not bonded to anything, just O2. Doesn't matter whether it's the first reactant or the second reactant. If it's on the reactant side, you need to go, hold up! That might be combustion. The nail in the coffin is you look at the other reactant. Does it have carbon and hydrogen in it? Maybe oxygen. Not always, but definitely carbon and hydrogen. If it has carbon and hydrogen in it, that is an organic molecule, and that is a combustion reaction. If you look at all the combustion reactions, every single one of them has an organic molecule and oxygen gas. Okay? Some of the single replacements on the other side of the worksheet also have oxygen gas. In fact, it's one of the more common ones you'll see in the long run. I tried to avoid it on this one, but you're going to see it in single replacements too. But you will never have a single replacement reaction that has an organic molecule in it as well. Okay, so if you have an organic molecule and O2, that's combustion, and the products have to be CO2 and H2O. And that's it for the combustion section. So write down all the answers because they're all exactly the same, and then turn your paper over and do single replacement. I'm going to, again, erase some stuff while you do that. All right, I am back again. We're looking at cation replacements on the back, and we need to talk about the difference between a cation and anion replacement. Okay? In a cation, well, first off, let's talk about the double replacement. In a double replacement reaction, you start with two compounds. Okay? Those two compounds trade their anions. The anion from the first compound goes to the second compound, and the anion from the second compound goes to the first compound. Okay, that's all that's happening. But in single replacement, you only have one compound. And so it could be the cation of that compound or the anion of that compound that's getting replaced. Thus the terms cation replacement and anion replacement. Okay, that means that you have to be able to recognize when it is a cation replacement and when it is an anion replacement. That cation replacement, the one we're starting with, well, to tell the difference, you have to look at your elemental. Okay, there's always one compound. In double replacement, there's two, but in combustion and single replacement, there's one compound. In combustion, it's going to be an organic. But in single replacement, whether it be cation or anion, it's just a compound. It's an ionic compound, and it's not going to tell you anything about whether this is an anion replacement or a cation replacement. You have to look at the elemental. In order for it to be a cation replacement, the elemental has to be something that forms a cation. Okay? Ammonium is never going to be in this spot because it can't really exist by itself. Okay, it's an ion. It can't exist by itself. It has to be attached to something. So what you're going to see here is always going to be either a metal or hydrogen. If this is hydrogen, H2, that is a cation replacement. If it's a metal, that's a cation replacement. If it is anything else, any non-metal, it is going to be an anion replacement, unless it's a combustion reaction. Okay, so if it's O2, if it's Cl2, if it's Br2, if it's P, if it's S, if it's C, whatever this is, other than a metal or hydrogen, if it's anything else, it has to be an anion replacement. Now, why does this matter? Well, it matters because cations cannot form bonds with other cations. Cation replacements, the cation has to replace the cation. So if we look at this compound, this is obviously the cation, and this is obviously the anion. Why this is important, since this is a cation, it means that these two have to swap. Now, you can keep the cation first, or you can try to keep the compound in the same spot. I'm just going to keep the cations in the same spot because that's what we've done before. Okay, so Na goes first, and K goes second. Okay, but the K, or the OH, has to be attached to the K. So I'm going to put the OH over here. Now, in one respect, cation replacements are nicer than anion replacements because metals never need subscripts when they're on their own. It's just the metal. However, most of our nonmetals, they're diatomics. That means you have to put the two. That includes hydrogen, which is obviously a cation, but you don't have to worry about it as much. anion replacements, you always have to remember that there's usually a 2 on the thing that's by itself. Only if it's a diatomic, though. If it's not a diatomic, don't worry about it. I don't know why I'm talking about this. It doesn't matter right now. Sodium doesn't need a subscript, so sodium just is written as is. It's no longer an ion. This is sodium metal. Then we have potassium, which is +1, and hydroxide, which is -1, so no balancing is needed for this. So that is the product. Now, I am going to do... I want you to attempt this one. Attempt this one. I will probably do one more, but I want you to attempt this one first. So pause this and take a crack at number 23. Okay, I'm going to do it now, so hopefully you've paused it. Aluminum is a metal, so it's a cation. Iron is the cation of the compound, and oxide, because O3 is not a polyatomic ion, oxide is the anion. So this is obviously another cation replacement. So I'm going to leave the aluminum in the first spot. I'm going to put the iron in the second spot. And the oxygen, the O, has to move. It has to swap. It was bonded to the iron. So now it's going to be bonded to the aluminum. But that means we need to figure out, is this charge balanced? Well, oxide is -2. Aluminum is +3. That's the wrong color, but we're going to roll with it. So that means we need to swap and drop. So we need 2 aluminum and 3 oxygen. Now, in this case, the subscripts wind up being the same, but that is not always the case. Don't rely on that too heavily. Okay, I'm going to go ahead and do... let's do 25. I'm going to pause this, write out 25. We'll do that, and then we'll move on to anion replacements. All right, here is number 25. Okay, so obviously cation replacement still, but we can tell that because this is obviously the first thing in the compound, so it's a cation. Magnesium is a metal, so it is also a cation. So the chloride here has to be our anion. So we're going to move the cation over. So H goes in the first blank, Mg goes in the second blank, and the Cl was bonded to the hydrogen, so it can't go here. It has to go here. So Cl has to go there. Cl is a -1. Magnesium is +2. So that means that we need 2 chlorines. Now, hydrogen is a diatomic. That means it cannot exist by itself. It has to be bonded to something. So this has to have a 2 subscript. Okay, any diatomic has to have a 2 subscript. Not just the hydrogen, but any chlorine that's by itself, any bromine, fluorine, nitrogen, oxygen, any of the diatomics, they have to have that 2 subscript. Okay, now I want you guys to pause this, work through these, check them against the key, and then the last part of this video we'll go through the anion replacements, which are pretty much the same as the cation replacements. But pause this, work through those, and then we'll get started. All right, time for anion replacements. Now, obviously, all of these are anion replacements. But again, I'm going to talk through why. I'm going to do 31, 33, and 37. Okay, so looking here, we have Li, which is the cation of the compound. But Cl is chlorine. Chlorine is a nonmetal. Chlorine cannot form a cation. So this is an anion, not a cation. Okay, likewise, oxide is an anion. So we are going to keep the cation in the same place, and I'm going to move it over here. And we are going to swap the anions. So O was bonded to the Li, so now it's going to go here. And Cl was by itself, so now it's going to go with the Li. Okay, now chlorine is a -1. Lithium is a +1, so those charge balance, and we do not have to add any subscripts. But O, oxygen here, is a diatomic, so we need to put 2 here to indicate that it is oxygen gas. It is oxygen by itself. Okay, now pause the video and take a crack at 33. All right, you did it? Okay, let's go. Now, Al in the compound is a cation, but again, Cl and N, they're both nonmetals, so they are anions, so this has to be an anion replacement. So, we are going to take the aluminum and move it straight over. N2 was by itself. N2 is not a polyatomic ion, just N. So N is now going to go with the aluminum. That's a -3. Aluminum, by the way, is +3. Both of which you're supposed to have memorized. And the Cl is going to go by itself. Okay, but Cl, again, by itself, can't be by itself, diatomic. We have to add that 2 subscript. Now for aluminum and nitrogen, or aluminum nitride, +3, -3, those cancel. We don't need to add anything to this time. And that brings us to the last one that I'm going to go through, which is N3P plus Br2. So Na, did I say N3? Na3. I don't remember. Okay. Na is our cation. We're going to just translate that straight over. P is an anion. And Br is an anion. So these two are going to swap places. So Br goes with the Na. The P goes by itself. Br is -1. Sodium is +1, so those cancel. We don't have to add anything. Phosphorus is not a diatomic. It's not a diatomic. So we don't have to add anything to it. Now, there are rules for most of these that govern the subscripts that they are supposed to have when they are by themselves. I'm not making you learn those. So just write P. That's it. Okay, P, S-E, T-E, C, S. I think that's all of them. Anything that's not a diatomic, that is a non-metal, just write it by itself. Don't try to put any subscripts on it. For the sake of this class and your sanity, it's not worth it. And that's pretty much it. You should now be able to go through and do the rest of these, finish up this worksheet, and yeah, that's pretty much it. Yeah, I don't have anything else. So I'm going to say have a good day. I'll see y'all in the next video, and bye-bye.